We are going to see the arid environment, the braided river and the meandering river and their deposits and the succession. Summarily, depositional environment in the arid region are the coarse material that are deposited on the alluvial fans. We will see that sand accumulates to form aeolian dunes and occasional rainfall feeds ephemeral lakes where mud and evaporite minerals are deposited. So, in the diagram we have got ephemeral lake, we have these sand dunes, these dots indicate sand, we have dry alluvial plain and the alluvial fans. These are the alluvial fans. Rivers coming from here from a slope and then it comes to a flat land and deposition happens and a fan geometry is produced. So, now let us look into the braided river and the meandering river situations. This is a hill region from which the rivers are coming, they join to form a bigger river. And then here is the braided pattern and then here we have the meandering pattern of the river. Here is the stratigraphic succession of the arid zone environment. The middle one is for the braided river deposits and the right hand side one is for the meandering river deposits. Let us start with the arid zone environment. In the bottommost we can find ephemeral lake deposits, thinly bedded couplets of mudstone and evaporites. As one moves up, one will find the alluvial fan deposits which can be matrix supported conglomerates deposited by debris flow. So, that means this ephemeral lake deposit is the oldest over which the alluvial fan deposits might come. So, over this the alluvial fan might be produced and so making possible that ephemeral lake deposit at the bottom, clay mud particles over which the coarse grained material conglomeratic alluvial fan material comes, over which lies the aeolian sand dunes, well sorted cross bedded sands. After this alluvial fan has developed, sand dunes might develop atop it, making a succession ephemeral lake deposit at the bottom, then comes the alluvial fan deposits and then comes the sand dune deposits. A braided river here is indicated by the river channel which converges and diverges and goes in this way. In the bottommost we can find the scoured base of channel over which we find the channel fill succession of cross bedded sands, decrease in cross bed set thickness, upwards fining up. This deposition is the thickest usually, but not always. Be very clear that the succession shown here, here and here are the idealized one. Worldwide in all the braided river deposits, worldwide in all the meandering river deposits and worldwide in all the arid zone environments, this may not happen as it is. Over which lies the overbank muds and thin sands with soils and tree roots. We know the level up to which the tree root can enter is called soil as per one definition of soil. So, we can say that the soil has developed over here. Now, let us look at the meandering river deposits. We start with the scoured base of channel. So, this is a common thing between the braided river and the meandering river, over which comes channel fill succession. Here also we got channel fill succession. So, it is a similarity. Here we get cross bedded sands and cross laminated sands. Same thing is also found here, cross bedded sand, and then there is a fining upward succession is found. Then over which comes the tree roots are visible. So, as per one definition of soil, this can be called as soil, over which lies the overbank muds and thin sands, soils and roots. We have seen here two words, channel fill, overbank deposits. We will see them in another context. In the channel fill deposits, sediments have got diverse sizes such as gravel, sand, mud, etc. We will now understand concept of avulsion. This concept works for both the meandering and the braided rivers. So, for the succession of the braided rivers and meandering rivers, this concept becomes important. What is an avulsion? Both in case of braided river and meandering river, the river shifts sideways and flow in the old channel becomes sluggish. Suppose this was a channel, but the river has shifted from old to the new, then in the old channel flow becomes sluggish. which means less water is flowing along the old channel. Most of the water has been diverted along the new channel. Now, what happens during the flood in the new channel? When a flood happens in the new channel, deposition also happens in the old channel. Because of this flood, deposition also happens in the old channel and leads to fine grained overbank sedimentation. Overbank sedimentation will mean fine sand, silt and clay particles, mostly fine grained materials, and they fill up old channels related to a different river course. This is a different river course now, but it gets filled up, and this process is known as avulsion. Let us look at the architecture of fluvial deposition in terms of rate of subsidence and the frequency of avulsion. The frequency of shifting of the river and fill up by the overbank deposit and the subsidence rate where sedimentation is happening. We start from this channel fill deposit, and this is the overbank deposit. Now, 4 situations can be considered. When there is more avulsion, we have less lateral migration, and when they have less frequent avulsion and more lateral migration, we can find that the channel fill deposits are more widespread. Here the channel fill deposits are more. Now, take a third situation, a slow subsidence rate when the channel fill is more than the overbank, and as per the diagram, the channel fill portions are significantly more, but if there is a channel fill less than the overbank deposit, which is indicated by the fast subsidence rate, one can see that more subsidence has happened. So, more sediments have been accommodated. There the channel fill deposits are separated, here they were close together. So, in this case the channel fill deposits are more spaced. Two terms we have come across, channel fill deposits and overbank deposits. Let us emphasize the point that the overbank deposits are usually fine grained sand, silt and clay particles, and they constitute the floodplain. When the river water spills and flood is created, fine particle in suspension gets deposited when the flood water is stagnant, leading to the overbank deposition. What about the channel fill deposits? A few basic things we need to know. In certain areas in the world, I am not writing the terrain, the overall geometry of the channel fill deposit is characterized by narrow sand ribbon shaped body, which is a few kilometer long, 80 to 150 meter wide and 1 to 5 meter thick. Just to give an idea the dimension of the channel fill deposit. These information, the numbers are from one particular terrain in the world, so the numbers can vary from place to place. What constitutes the channel fill deposits? They are consisting of dark grey organic rich mud and without any visible sedimentary structure. Again, this part without any visible sedimentary structure, and this information is coming from a coastal wetland area. One important point to understand, so far I have shown the channel fill deposits in the non-marine environment, but do not think that channel fill deposits, all the channel fill deposits worldwide are product of non-marine deposition. No, in fact, channel fill deposits can also be found from the deep marine deposits. Just one reference is given and there are other reference also. In this connection, we need to know a little bit about the channel sands. The sands that accumulate in stream channels are coarse, often silty, immature and poorly sorted. They occur as elongated thin bodies, sinuous and prismatic or lenticular in cross section. This is a lenticular geometry. So, in cross section, in vertical cross section, the channel sands can look like this. The term shoestring sand is there in the literature, which includes the channel sands. And these individual channel sand bodies can coalesce, that means can join to form complex sheet deposits, which are often only partly preserved and partly destroyed. Here is an idealized sequence and structures of alluvial channel deposit. The succession of alluvial channel deposits consists of the braided river with probable channel bottom deposits at the bottom shown by A. The second unit from bottom B consists of deposits of large meandering rivers, and it consists mainly of sand and gravel, but there can be pockets of lake clay deposits. Unit C consists of small meandering river and strongly branched river deposits shown over here. The contact need not be horizontal, but it can be wavy, and the swamp and the peat formation can happen at the topmost region shown by this black color. Again, do not try to compare all the alluvial channel deposits with this one. This what we can call is an ideal one. The detail one can read here. Lake successions. What is an ephemeral lake? Few slides back this term came. Periodic drying happens in an ephemeral lake and mudstone evaporite couplet develops in stratigraphic succession. Couplet means an alternating situation. Mudstone evaporite. In this way, a succession can develop in case of ephemeral lake where periodic drying happens. When this drying happens, then the evaporite gets deposited. These are the different kinds of salts. Evaporites are salt deposition after the water evaporates. Let us look at the succession now. The deeper lake deposits are laminated dark shells and thin turbiditic sands and silts. So, one observation here is we get the fine grained sediments, and since dark shell is referred, that means it is a anaerobic condition over which lies a shallow lake deposition, wave rippled sand, and this is much thicker portion, and over which lies a shallow lake deposits, beach and or lake delta sandstones are produced. This is typical succession for freshwater lake. Alluvial fans were referred in this discussion. Let us look at the typical deposition of the alluvial fans. They are the cones of detritus that form at a break in slope. Imagine from a hill a river is coming down and it comes to the nearly flat topography. That is the meaning of the term break in slope at the edge of an alluvial plain. Deltas and large distributary river systems are included when we are going to talk about the alluvial fans, and if the alluvial fan is very vast, the word mega fan is also there. Sedimentary bodies consisting of talus and debris flow deposits are called the colluvial fans. That is another use of the term fan. Three kinds of fan can be discussed: the debris flow fan, the sheet flood fan, and the stream channel fan. What is typical of the debris flow fan? Here debris flows form lobes on the fan surface. So, by bold color that debris flow is shown and they are forming lobes. These are the lobe geometry. What happens in case of a sheet flood fan? The sheet floods spread out over the part of the fan surface. So, a sheet geometry can be found and clearly it is more spread. That is why the term flood has been used. It floods and spreads over large area. Compare this area of spread from that area of spread from the debris flow fan, the spread is much more. Now, the third variety is a stream channel fan. Here what happens? Stream channels change positions on the fan surface through time. This one is the fan surface and over which the stream channels, and they change their position over time. Alluvial fan need not be classified strictly into debris flow fan or sheet flood fan or a stream channel fan. Mixed examples are also there. Anyway, we now come into the successions. Naturally, in the debris flow alluvial fan, the debris flow material is dominated and we have matrix supported poorly sorted conglomerate beds. In case of a sheet flood alluvial fan, we find an alteration of conglomerate and sandstone. Conglomerate sandstone, this kind of alteration is developed here. This is the conglomerate layer, then there is a thin sandstone. Again here is a conglomerate layer up to this much and here is a thin sandstone layer, and the conglomerate layers are thick whereas the sand layers in between are thin. Now, let us look at the stream channel fan. In this case, the sandstone deposits are thicker. We have here also conglomerate sandstone, conglomerate sandstone, conglomerate sandstone and conglomerate. is that we get finding upward succession. What has been said is a general information, and the exact information might vary from alluvial fan to alluvial fan. We are going to see hydrostratigraphy. Unlike lithostratigraphy and biostratigraphy, hydrostratigraphy nomenclature and the division is informal. We have two units involved in hydrostratigraphy. One is aquifer and the second one is aquitard. Let us find the meanings. Aquifer is a formation that contains sufficient saturated permeable materials. Here material means rock materials, or it can be unconsolidated sediments that can yield significant quantities of water in wells and springs. Let us try to understand. This definition I have taken from the book by D.K. Todd. In geohydrology books, the word formation which is used has a different meaning from what has been used in lithostratigraphy. We have to be very clear that in lithostratigraphy the way formation is defined, and in geohydrology or even in well logging, when we use the word formation, their meanings are different. Here formation means rock or rocks and unconsolidated sediments, if any, under consideration. So, any rock or unconsolidated material that contains sufficient saturated permeable material. Sufficient means how much? No quantitative definition is given. Within the entire formation, is it that the 5% of material which has saturated permeable content, or is it 10%? That percentage is not given clearly. So, the definition of aquifer does not involve quantitative meaning. Saturated permeable material. Here, as I told you, the material will mean here either rock or unconsolidated sediments. Now, let us try to understand what is permeability. Ease of flow of any material through a medium is permeability. And here what are we dealing with? Water flow. So, and medium in this case is either rock or rocks and unconsolidated sediment. A highly permeable material means fluid can flow easily through it, water can flow easily through it. Low permeable material means it is difficult for water to flow through that rock or unconsolidated sediment. Zero permeability of the rock is possible if a rock has got no interconnected pore space, and if it is unfractured, then the rock has practically zero permeability. What is the meaning of pore space? In clastic sedimentary rock, there can be several grains and there can be space inside. This is the pore space. It can be devoid of water, can be partially filled up with water, or it can be completely filled up, what is called saturated with water. Saturated means mostly filled up. So, in this case it is mostly filled up with water. So, the presence of pore space is required and they have to be interconnected so that permeability can arise. If there are pore space but which are not interconnected, then permeability is practically zero. From the pore space we can define a term called porosity, and from interconnected pore space we can define the term effective porosity. Now, having sufficient permeable material with effective porosity does not guarantee that the rock or the sediment is aquifer. It has to be saturated with water. There has to be water present significantly within the pore space. It should not be vacant. To what amount it is required? So much of water is required so that it can yield significant quantity of water to wells and springs. The aquifer can be punctured manually by drilling a well, the water well, or the topography can intersect the aquifer where springs will manifest. Now, in these springs and in these wells, there should be a significant quantity of water available. Now, significant means how much? How many liters per day? How much should be the stock? that is not stated. So, again there is a second degree of qualitative definition, significant quantity, how much, no quantitative definition is available. There are other names of this aquifer, it can be water bearing formation or it can be groundwater reservoir. Sandstone can define an aquifer if there are interconnected pore spaces and that is mostly filled with water, to the extent that if a water well is drilled or the topography intersects the sandstone layer, then good amount of water is available. Well sorted sediments such as sand can have high amount of porosity, and if the pores are connected, it will lead to a high amount of permeability. So, makes a good chance for an aquifer condition. Consider dry rock, that means sandstone, but there is no water present within it, then it cannot be called as an aquifer. Consider an igneous rock or a metamorphic rock which is unfractured. If there is no fracture, then there is no fracture permeability. Fluid cannot pass easily or water cannot pass easily across the rock. In that case, that unit cannot be called as an aquifer. If there is an igneous or metamorphic rock which is severely fractured in one set or more than one set, in that case there is a good chance that water can be present, stored within the fracture or the joint. So, in that case the rock can be called as an aquifer. Hard rock such as igneous rocks and metamorphic rocks can also be in certain cases considered as an aquifer if there are fractures or joints, more than one set or simply one set. We are going to see the second hydrostratigraphic unit, which is known as aquitard. What is an aquitard? It is a saturated but poorly permeable stratum. What does that mean? There are pore spaces available and that pore space is saturated or significantly filled up with water, but the material is poorly permeable. That means these pore spaces are not interconnected, which means the effective porosity is reduced and the porosity is having moderate to high value. Since the permeability is reduced, so it impedes or it precludes or it stops or it prohibits the groundwater movement. Therefore, if you drill a well in an aquitard material or the natural topography cuts this aquitard material, it will not yield freely significant water, and an example of aquitard material can be clay. Remember, clay has two definitions. One is mineralogic, that it is a hydrous aluminosilicate and there are a group of clay minerals. Example of clay minerals include illite, smectite, montmorillonite, kaolinite. There is another definition of clay, the sedimentological definition as per the Arden-Wentworth scale. Clay is very fine sized sediment of any composition where the diameter of the grain is less than 1/256 millimeter. In this definition, in this sedimentological definition of clay, we are not specifying what is the chemical composition of the clay, which can be anything. In this case, once we are saying clay, we are implying the sedimentological definition and we are not implying the mineralogical definition. Now, if we look at the hydrocarbon geoscience textbooks, aquitard has equivalent names such as seal or the cap rock, because it will not permit fluid such as hydrocarbon to flow across it. So, what can be visualized in hydrostratigraphy is that there can be aquifer layer and there can be aquitard layer. In geohydrology, besides aquifer and aquitard, you will find terms aquiclude and aquifuge. However, we do not use these terms in hydrostratigraphy, but it does not mean we will not use in our work. Depending on the requirement, we can use aquiclude and aquifuge words. And as per hydrocarbon geoscience, what can be the equivalent term of aquifer? In geohydrology, aquifer is a place where water is stored, and in hydrocarbon geoscience, it is a place where hydrocarbon is stored. So, we can call it a reservoir rock or simply a reservoir. I have already said groundwater reservoir is an alternate term of aquifer and water bearing formation is another term. However, it is recommended instead of using these words in stratigraphy or hydrostratigraphy or in geohydrology, one should use the word aquifer. Now, once we say aquifer and aquitard as the two hydrostratigraphic units, do not have this notion that everywhere on the earth the material can be clearly divided into a layer of high porosity and high permeability, where water can be extracted to a significant quantity through wells and springs, and then there can be a layer where high porosity may be there, but the permeability is significantly reduced. There can be patchy occurrence of aquifer and aquitard, or patchy occurrence of these two dissimilar kinds of rocks. For example, in this rock material I can have patches of clay and they are discontinuous, and this clay precludes groundwater flow, and in the sandstone it permits the water flow. So, here we cannot clearly demarcate a single layer calling it as an aquitard. Meandering river, we do see such depositions. So, in this case, this simplistic diagram that aquifer is a single layer and aquitard is another layer maybe capping the aquifer is not possible to define. Aquifers and aquitards. Note that in case of lithostratigraphy and biostratigraphy, we make correlation. Certain lithostratigraphic units such as formation in one place, tens of kilometers away in a basin there is a deposition and another formation, and we say they are time equivalent. Can also be done in biostratigraphy based on fossils. But in case of hydrostratigraphy, there is no such need that an aquifer material sand is it time equivalent to another aquifer and they will be linked. Here the prime concern is water flow, and it is also true that sandstone deposited in two basins nearly at the same time, one of them can become an aquifer and another one may not become an aquifer. Therefore, we can say time equivalent sedimentary rocks may not always be correlated as a single hydrostratigraphic unit. And what do I mean by say hydrostratigraphic unit? So, the sentence can be as a single aquifer, or I can say as a single continuous aquitard.